Good evening, all. Good evening, all. Welcome to the afternoon session of control system. So now, just we'll recall the things what we have discussed so far, and today we're going to start the another new topic. So in the last class, we have we have discussed about the uh, we have discussed about the time response analysis, right? So we have started our discussion on the time response analysis in the last class. So today we'll just recall the previous things what we have discussed in the time response analysis, and we'll start the new topic. Is that clear? So I hope that everyone listening to me and the screen is visible to all. So I'm just starting the today's session. So so when we talk about the time response analysis, so particularly in the case of time response analysis, what we are doing, particularly we are dealing with the whatever the output we are having, we are dealing with the function of time. Is it clear? In the time response analysis, whatever the output here we are having, we are dealing that output with a function of with respect to time, right? So in the previous class we have discussed about the response for a different response for a unit step input for different types. For example, for a first order system, we have discussed the response. We have we have observed the response for a first order system for unit step input, and also we have observed the response of a second order system for uh, unit step input for different cases, for under damped system, for over damped system, for critically damped system. So these are the things we have covered so far, right? So we have covered these expressions for under damped system, over damped system, critically damped system, and also we have completed this and also we have completed these all responses. Now we'll started our discussion on the time domain specifications. So here particularly what is the main use of this time domain specifications? For the desired performance characteristics of a control system are specified in terms of this time domain specifications. So whatever the desired characteristics of a control system is there, which is specified in terms of time domain specifications. Actually what happens here, whatever the physical systems here we are having, particularly I'm talking about the electrical system. This electrical system whatever we are having, it consisting of energy storage elements. So this energy storage elements whatever we are having, they exhibit they can't exhibit respond they can't respond instantaneously, and I will exhibit transient responses. Is that clear? Whenever they are subjected to inputs or any some kind of disturbances. So the desired performance characteristics of a system of any order may be specified in terms of transient response to a unit step input. So the response of a second order system for unit step input with various damping ratio is shown here. Is that clear? So here it is clearly shown in this picture that the response of a second order system for unit step input for various damping ratios. I have already said that what do you mean by the damping ratio. It is nothing but actual damping to critical damping. So here it is clearly visible here on the screen that for the different zeta values, this is the waveform, this is the output response what we are having here for a unit step input. Is it clear? As zeta equals to 1, that is the critically damped system, we are having this kind a faster response what we are having. So this is the final value 1, whatever here we are having is it a final value. So when system is critically damped, the response is faster, right? So the transient response of a system to a unit step depends upon the initial condition. Therefore, to compare the time response of various systems, it is necessary to start with standard initial conditions. Is that clear? The most practical standard is to start with the system at rest, and so output and all time derivatives before t equal to 0 we supposed to consider here. The the transient response of a practical control system often exhibit what happens, it will exhibit some damped oscillations before it reaching to the steady level, before it reaching to the steady state. So a typical damped oscillatory response of a system is shown in particular figure. Here it is clear, it is shown in the figure 2.14. So this is the response of a which system, second order system for a underdamped case. Is it clear? For underdamped case, this is the response what we are having. See here in the previous class we have derived the expression for this one. So this is the response what we got for a underdamped second order system for a unit step input. So this I have considered, this we have considered now. So now what happens here, when the response reaches the steady state value, what happens when the response reaches the steady state value, it will it will it will exhibit some sort of what we say here, it will exhibit some sort of oscillation. See here. So now this is the response from 0, from the initial state. What happens, it is slowly rising, and when it reaches its final value it exhibits some oscillations over here. Is it clear? So the allowable error, I mean the tolerable oscillations whatever here we can allow, it can be tolerated is 2% to 5% is allowable. Is it clear? So this we calling it as a steady state error. Is it clear? Now first of all here particularly the response. So whatever the time take, what do you mean by the transient response? The transient response is nothing but what the time taken by the response to reach from the initial value to its steady state value. So in this particular part we calling it as a transient response. Is it clear? Remaining, once the transient response is died out, this is nothing but steady state response. This is nothing but a steady state response, and this part whatever you are having is nothing but a transient response. Now the transient characteristics of a control system to unit step input is specified in terms of the following time domain specifications, right? So here what are the time domain specifications we are having: delay time, rise time, peak time, maximum peak overshoot, settling time. So these are nothing but the time domain specifications. So first of all we'll discuss about the delay time. What do you mean by the delay time? What do you mean by the delay time? From this response, what is delay time? So it is nothing but what the time taken for a response to reach 50% of the final value for a very first time. So it is nothing but to the time taken by the response to reach 50% of the final value for the very first time is nothing but delay time. Rise time is nothing but what the time taken for a response to rise from 0 to 100% for the very first time. Is it clear? Now when we talk about this rise time, it will be different for the different systems. For a underdamped system, the rise time is calculated from 0 to 100%. If it is a overdamped system, the time taken by the response to reach to rise is from 10% to 90%. If it is in the case of a critically damped system, it will be 5% to 95%. So depending upon the type of damping, the rise time will be varying. So for underdamped system it will be 0 to 100%. In the screen on this screen it is underdamped, the response of underdamped system. So for the underdamped system we supposed to take 0 to 100%. So that is the thing what we have taken here. It is from 0 to 100%. This is the rise time what we are having. Now when we talk about the peak time, it is the time taken for the response to reach the peak value the very first time, or it is the time taken for the response to reach the peak overshoot. So when we look at here, so this is a peak value, so this is the TP. Fine. So what do you mean by the peak time? The time taken by the response from 0 to reach its a peak value, we calling it as a peak time. Is that clear? um, Fine. Next, peak overshoot. So what do you mean by the peak overshoot? It is nothing but it is the ratio of maximum peak value to the final value. It is a ratio of maximum peak value to the final value, where the maximum peak value is measured from the final value. See here, when one second, when we look at this particular waveform, here it is clearly visible that, see, this is the peak overshoot, this is the peak overshoot, so this is the final value, this one is the final value, and moreover above, behind one, whatever here we are having, this is the peak value. So what do you mean by the peak value? It is nothing, peak overshoot is nothing but what? It is nothing but the ratio of the maximum peak value to the final value, maximum peak value to the final value. This is nothing but a MP, I mean the peak overshoot. So final value, here we are having a C of infinity. C of infinity is nothing but final value, that is C of t. Why we are considering that is C of infinity? Why? Because we can't judge that final value at this instant. Our response will reach this final value. We can't judge like that. So for that purpose, we simply it is calling it as a C of infinity for the final value. And next, maximum value C of t is nothing but C of tp. I mean the peak value. So what will be the maximum peak overshoot here? C of tp minus C of infinity by C of infinity is by C of infinity into 100. This is the maximum peak overshoot what we are having. Is it clear? Now when we talk about the settling time, already I said that the allowable error, I mean the tolerance value is 2% to 5%. So uh, what is settling time? It is defined as the time taken by the response to reach and stay within its specified error. I mean the error here is 2% to 5%. Above the 5% will be not tolerable. Is it clear? It's supposed to be stay within this error, within this tolerable error. Um, it is usually within it the specified error, and it is usually expressed as percentage of final value. The usual tolerable error is 2% to 5% of the final value. Yeah, that is the same thing I'm talking. So this is about the settling time. So these are the five time domain specifications we supposed to discuss now in the session. uh, so particularly with this, we can find out the performance characteristics. Is it clear? We can find out the performance characteristics here. So first of all, when we talk about, first of all, I want to find out the expressions for the time domain specification. Now here I am taking the rise time. I am talking about the rise time. So the unit step response of a second order system for a underdamped case is given by what? This is the thing what we are having, right? C of t equals to 1 minus e power minus zeta omega n t by omega n into tr by under root 1 minus zeta square sine omega dt plus theta. So this is a response of a second order underdamped system, right? Underdamped system which is a function of time. Is it clear? So now here I am supposed to find out the rise time. So I'm just redefining the time t equal to tr. Is it clear? And c of t equals to c of tr. Is it clear? Final value in the sense what? Here we are having the final value is 1. Is it clear? This is the final value. Here the final value what we are having is 1. So now I supposed to find out the expression for the rise time here. So now so what we can say here, c of tr equals to 1 minus e power minus zeta omega n tr by under root 1 minus zeta square sine omega d tr plus theta equals to 1. This is nothing but the final time, final value. So now by substituting, by simplifying this, finally this is the equation what we have. Is it clear? Just I am moving what I am doing here is I am just moving 1 to this side, so it will be a 0. So finally this is the equation what we are having here. Now since e power minus zeta omega n tr which is not equal to 0, the term sine of omega d tr plus theta equals to 0. So where phi is nothing but what? 0 comma 5 comma 2 pi comma 3 pi, so and so, sine phi equal to 0. So finally what will be the, from this, and from this we can find out the rise time, where rise time is nothing but what? Pi minus theta by omega d, where theta is nothing but what? From this we can construct the right angle triangle. So from after constructing the right angle triangle, we find out the t tan theta, that is nothing but under root 1 minus zeta square by t theta. So what will be the theta? Theta is nothing but tan inverse of under root 1 minus zeta square by zeta. Just substitute over here. So finally this is the TR what we are having, that is nothing but 1 pi minus theta, where theta is nothing but what, tan inverse of under root 1 minus zeta square by zeta by omega n under root 1 minus zeta square. So this is the rise time what we are having, expression for the rise time. Similarly we can find out the expression for the peak time. Just check it once, the expression for the rise time, everyone. Just everyone go through this. Everyone is clear with the expression for the rise time, right? Check it once, everyone. Any doubts, please you can ask me regarding this. Any doubts, you can ask me regarding this. Just I will giving you your 1 minute time. Just please go through this equation, everyone. హలో ధీరజ్, క్లాస్ జాయిన్ అయ్యావా? క్లియర్గా ఉందా అంతా? ఏం ప్రాబ్లం లేదు కదా, అర్థమవుతుంది కదా క్లియర్గానే? ఓకే, మళ్ళీ జస్ట్ కన్ఫర్మేషన్ కోసం ఓకే. Now okay, fine. Now when we come back to this peak time, see, we suppose how to find the expression for the peak time. To find the expression for the peak time, first of all what we supposed to do, we supposed to differentiate the c of t with respect to t and equate it to 0. So differentiating c of t with respect to t and equating it to 0. So we know that the step response of a 100 amp per second order system is given by this one. Is it clear? C of t equals to 1 minus e power minus zeta omega nt by under root 1 minus zeta square sin omega dt plus theta. So this is the thing what we are having. Just I am differentiating this equation with respect to t. Finally what we are having, so this is the equation we are having. I'm just putting omega d equals to under root omega d equal to omega n under root 1 minus zeta square in this particular expression. So finally after putting this omega d in this equation, finally what I'm getting is, finally by simplifying here, this is the equation what we are having, omega n by under root 1 minus zeta square e power minus zeta omega nt of sin omega dt plus theta cos theta minus cos of omega dt plus theta sin theta, by simplifying this one. So finally what we are having, omega n by under root 1 minus zeta square e power minus zeta omega nt sin of omega dt. Is it clear? So now again the same thing for this equation whatever having, we know that this exponential term is not equal to 0 and the sin term whatever here we are having is equal to 0. So for when phi equals to 0, phi equals to pi, so pi equals to 2 pi, when it will be, what happens, just substituting it this values in this term. So what we can say here, omega d plus theta, omega d plus dp equals to will be omega dt omega d into tp equals to pi here we are having. So finally peak time tp equals to what, pi by omega d, where omega d we know that is omega n under root 1 minus zeta square. So finally peak time is nothing but what, pi by under omega n into 1 minus under root 1 minus zeta square. Just please everyone check this expression for the peak time. If any doubts you can ask me regarding this. everyone please check it once. Check the expression for the peak time once, everyone. See, these expressions are very important. Again once again repeating these expressions. Whatever we are discussing is very important. So any one expression they might ask in the exam, and or else we'll have some problems based on these expressions. Some problems we can have in the exam. So you have to remember these formulas. What is the formula for the rise time? What is the formula for the peak time? You supposed to remember this. So just please everyone once go through the expression. It is a simple mathematical analysis what we supposed to do over here. Yeah, it's clear everyone. Shall I move to the next problem, next topic? So similarly we supposed to find the expression for the peak overshoot. We know the formula for peak overshoot. In the last class I have discussed it. C of Tp. In the previous discussion we came to this one. So percentage peak overshoot equals to C of Tp minus C of infinity by C of infinity into 100. We know that C of Tp equals to peak response at T equal to Tp, and C of infinity is nothing but what? Final steady state value. I already said that why we are taking the C of infinity. It is clear. So C of infinity is nothing but what? Final steady state value. So the unit step response of a second order system is given by what? So this is the response what we are having. Just substitute the values of t of t equals to infinity in this equation. So it will be 1. If we substitute t equals to Tp, this is the expression. This is the expression what we are having, right? When we substituting this t equal to Tp over here, Tp is nothing but what? Tp is nothing but peak value, peak time, peak value here. So just substitute this t equal to Tpo in this equation. So finally this is the expression what we are having, 1 plus e power minus zeta into pi by under root 1 minus zeta square. So now we supposed to find out this percentage peak overshoot, that is percentage mp, that is nothing but just substitute the values of c of Tp and c of infinity o in this equation. So finally we having the expression e power minus zeta into pi by under root 1 minus zeta square into 100. So this is the formula for percentage peak overshoot. It's clear. Here nothing to do, a simple mathematical analysis we supposed to perform here. Next, when we coming to this settling time, just look at this peak overshoot, everyone please. Expression for the peak overshoot. Please everyone look at the expression for the peak overshoot. A simple mathematical analysis we supposed to carry on here. If any doubts you can ask me. Yeah, now when we coming to this settling time, so how come we can find out the expression for the settling time? See, whatever the second order system response here we are having for underdamped case, for a unit step input it having two components. See, with this second order system response, whatever the equation here we are having, it having two components. One is the exponential component, right, and another one is the sun time. So two components here we are having. Just I will go once again, I will just moving to this uh, response. So this is a response what we are having. It having two components. One is the uh, exponential component, another one is the sine component, right? Two components here we are having for this particular response of a second order system. So one is the exponential component, it is the decaying. So decaying exponential component here we are having, another one is the sinusoidal component, right? So when we talk about the decaying exponential term, it dampens or reduces the oscillations produced by the sinusoidal component. So whatever this decaying component here we having, it dampens or reduces the oscillations which is produced by the sinusoidal component. So for that purpose what we are doing, uh, decide we are deciding the settling time by the exponential component. Is that clear? So the settling time can be found out by equating exponential component to the percentage tolerance error. Already we having some percentage tolerance error, that is 2% to 5%, right? So particularly here what we doing, we deciding the settling time, we are finding the settling time by exponential component by equating this exponential component to a percentage tolerance errors. So for example, for 2% tolerance error band here we are having, for 2% tolerance error band, t equal to ts, at t equal to ts, I'm just redefining the time t equal to ts, settling time I'm talking about. So what I'm doing here, I'm just redefining the time t equal to ts. So it will be what, e power minus zeta omega n t omega n ts by under root 1 minus zeta square. It is what, 2%, so 0.02 here I am considering. So for least values of zeta, what we can take here, e power minus zeta omega n ts equals to 0.02. Just I am taking the natural logarithm over here. So after taking the natural logarithm, if I find the value of ts, that is nothing but what, 4 by zeta omega n, what we are having, ts equals to 4 by zeta omega n. Is it clear? So for the second order system, the time constant will be what, 1 by t equals to 1 by zeta omega n is the time constant. Is it clear? So finally what will be the settling time here, what we can say here, ts equals to 4t is the settling time, ts equals to 4t will be the settling time. Is it clear? This is for the 2% tolerance error. If we are having a 5% error, what will be the tolerance error? Just look at here, what will be the settling time for the 5% tolerance error? Please everyone, try to solve that. If we are having a 5% tolerance error, what happens? What will be the ts settling time? What happened? What is the value? What is the settling time? ts equals to what we can have. So for the 5% tolerance error, ts will be what, it will be 3t. I hope that it is clear. If we having a specified percentage error, settling time, if you having if in general for a specified percentage error, the settling time can be calculated, evaluated by using what is the formula, ts equals to, so this is the formula we supposed to take into consideration for calculating the settling time. I hope that it is clear for all. Just we'll look at some problems based on this topic. Now here we are having one example. Obtain the response of a unity feedback system. Obtain the response of a unity feedback system whose open loop transfer function is g of s equals to, what we are having is 4 by s into s plus 5, and when the input is unit step input. So what we need to find out here, we supposed to find out response of a unity feedback system. We supposed to find out the response of a unity feedback system whose open loop transfer function, this is the open loop transfer function they have given, and the input is unit step. So we supposed to find out the response. So this is the block diagram they have given. So just find out the response for this particular system. How to find now? So first of all, they have given the open loop system. We supposed to find out the transfer function of a closed loop system, right? So unity feedback is there. So what will be the transfer function here? C of s by r of s is nothing but this is the transfer function we are having. So this is the transfer function what we have. Now we know the input r of s is how much? What, one second, r of s is what we are having is, yeah, unit step. So r of s is 1 by s. R of s is 1 by s what we have. So now what we need to do by yeah, any doubts? Yeah, you can ask if any doubts. Anyone, any doubts? So one of the student trying to ask the doubts, but he is not capable to uh, his voice is not audible. They can message me, they can text me, no problem, they can text me. So if any doubts you can text me, no problem. Partho is trying to ask some doubt. Is it clear? Who is the? Is it clear, Partho? Partho Sarkar. Just ask me if you not possible if it not possible to ask, you can text me, no problem. Mr. Partho, what is your doubt? You can ask me. Make it fast. Okay, okay, no problem. Okay, fine. Particularly now we're supposed to find out the response of a unity feedback system, right? So first of all, what we're supposed to do is, here what I'm doing is I'm just finding out the transfer function of a closed loop system. And now what we're having, C of s equals to r of s into 4 by s plus 1 into s plus 4. This is the equation what we're having. We know that r of s is nothing but 1 by s. Why? Because it is a unity uh, unit step input is the input what we are having. Input is unit step, so rfs is nothing but 1 by s. Now I'm applying the partial expansion for this one. I'm finding a, b and c with the normal procedure what we're having. So finally what I having, the time domain response I supposed to find out, right? So I supposed to apply the inverse Laplace transform. So c of t is nothing but what, inverse Laplace transform of c of s. So finally, by doing the simple mathematical analysis, this is the response. So just everyone go through this problem. Everyone, please, I'm giving 1 minute time. Just go through this problem once, everyone. Any doubts you can ask me. It is clear. I hope that everyone clearly got idea about this one, right? Shall I move to the next problem? These problems are very important. I'm one more time stretching on this one. Is it clearly understandable for all, or once if you want means once again I will repeat this. You can please respond to me, are you understanding or not? If not means again I will repeat the same. Yeah, fine. I hope that everyone clearly understood the questions, right? Next problem. When we look at the next problem, a positional control system with velocity feedback is shown in figure. So this is a positional control system with velocity feedback is shown in figure. What is the response of the system for unit step input? I'm asking this. I hope that everyone will solve this. Just solve this and tell me the answer. So here we are supposed to find out the response of a system for unit step input. Just everyone try to solve. A positional control system with velocity feedback is given, uh, and they asked us to find out the response of a system for unit step input. Just please any one of you, please everyone solve this and tell me the answer. What is the answer? Any one of you? Please respond to me. Anyone, please give me the answer for this question. So first of all, what we supposed to do? We supposed to find out the closed loop transfer function for this one. So this is the open loop transfer function. So and here we are not having a unity feedback system. Is it clear? Here we are having a positional control system with velocity feedback. Is it clear? So now and that RFS input is nothing but step input. Now that is nothing but RFS is nothing but what? RFS is nothing but 1 by S. Is it clear? So this is RFS what we are having. So now C of S by R of S is nothing but, so finally this is the closed loop transfer function here we are having, and R of S is nothing but 1 by S. Just substitute over here. So 1 by S into 100 by, so this is the overall transfer function what we are having. So C by S is equals to 1 by S into 100 by S square plus 2LS plus 100. So by now again by the partial fraction expansion here what we are having, we are supposed to find out the unknown terms here A, B and C over here. So A equals to, by solving this we are having A equals to 1, and by doing the cross multiplication we can find out for this we can find out B and C here. B equals to minus 1 and C equals to minus 12 over here. So finally the response here, C of S equals to what? This is the response. Finally by doing the simple mathematical analysis, this is the equation we are having. Now I am applying the inverse Laplace transform for finding out this time response, that is C of t. So C of t equals to nothing but what? Inverse Laplace transform of C of S. So finally this is the response what we are having. Is it clear everyone? Any doubts you can ask me regarding this. Now when we talk about the next problem, so this is the next problem what we have, example problem what we are having. Here the response of a servo mechanism is given. They given the response. when subjected to the unit step input, obtain an expansion for a closed loop transfer function. Determine the undamped natural frequency and damping ratio. So here we supposed to determine uh, undamped natural frequency and damping ratio. We supposed to find out. We supposed to find out omega n, and we supposed to find out zeta. Just solve this. Just solve this problem. Please everyone solve this problem. Please everyone solve the problem. Here we supposed to find out omega n and zeta value. We supposed to find out. Already we having the time response. Is it clear? Time function, the response we having, c of t we having. So we supposed to apply the Laplace transform for this one. Is it clear? So this is the equation what we are having. Unit is r of s, what we step input, that is r of s equals to 1 by s. So c of s by r of s is nothing but what? 600 by s square plus 70s plus 600. Now just we comparing with this the whatever the equation here we are having, I mean the closed loop transfer function what we are having, we are comparing with the standard second order equation. Is it clear? So from that we can find out omega n, where omega n square equals to 600. So from that we can find out omega n, that is nothing but what? Undamped natural frequency. And when we and from this also, and from this we can find out the value of zeta. Is it clear everyone? So for now, for today I will stop here. Any doubts you can ask me regarding this, any doubts in this particular problems which we have solved today. If you have any doubts, please ask me. For now I will stop here. Please ask me if you have any doubts regarding this. You can text me here. Regarding that, some of the students having this doubt, you can go through this one. See, Laplace transform of the signal r of s, is it clear? For a unit step input, it is 1 by s. Time domain equation of a signal r of t, it is 1. So most of the students having this doubt. So Laplace transform of this particular signal r of s is nothing but 1 by s for unit step input. For a step input we are having a by s. Is it clear? So some of the students have asked that question. Fine, just you look at that particular table, you will have a clear idea. So please don't get confused. So if you for your sake only you will get confused, I thought, and I am discussing from that particular textbook only directly. So if you go back go to the introduction, then you will find out some of the tables. From the tables you can clarify your doubts. So regarding this r of s, just you people go to that particular tables. where you can find out, where you can will get clarified with your doubts. Any doubts regarding, any more doubts regarding this topic? Fine. Yeah, I will stop here. Thank you all. We'll continue in the next class.